This will be the one on Google Classroom. All right, so we'll zoom in right there. All right, so the atom and periodic table notes is what we're going to do. So in your notes, and today is 1/26/17, Thursday. All right, so the very first thing that we're going to do is our EQ. And our EQ is, how is the periodic table organized? And that is what we are looking at today. And hopefully by the end of this, we'll be knowing how it's organized and be looking at the atom itself and the structure of the atom, because the periodic table is organized based on the structure of the atom. So the periodic table, one of the neatest things about the periodic table to me is that everything in existence, everything that's matter, right? Anything that has mass and takes up space is one or more of those elements on the periodic table. Everything. Everything that's matter. So you, your body, your cells, the table, the computer, the desk, the air, the stars, the other planets, our whole planet, the Earth itself. All of that is made up of some combination. It's kind of like the alphabet for matter. Because, you know, like an alphabet, 26 letters, right, in the English language. Every word that you know is some combination of those 26 letters. And that's it. Those 26 letters in some combination. And same thing, everything in existence is on that periodic table. And another kind of deep thought that I was thinking about on the way to school one day, because when I drive back and forth, I think kind of deep thoughts sometimes. But I thought about this is, 500 years ago, they still had everything in existence. All the matter that existed then is matter that we have now. So why is it, I'm going to pose this question to you, why is it that we have computers and phones and fast cars and things like that they didn't have 500 years ago? Because of technology. And where does technology come from? It comes from here, doesn't it? It comes from smart people, right? It comes from an idea, is exactly right. So you have an idea, what if? You have enough people that have those what if questions, and instead of just saying what if and then saying, oh yeah, not going to do anything about that, they educate themselves or find education and find somebody else that's done something like it, or they're paving the way. And because they do trial and error, they do the scientific method, they ask a question, they research it, they try it, they may fail, but a lot of times scientists have found out more from failing than from actually succeeding, because they'll fail and fail and fail and fail, and they learn a lot, and then they'll succeed. And then we have new technologies and new educations and new patterns that we find out. So, but the weird thing is even 5,000 years ago, everything that we have right now existed. Isn't that weird? So 5,000 years ago, everything that is in existence now, matter-wise, was in existence then, just in different combinations. Why didn't they? Technology, education. They didn't have, at that point in history and time, they didn't have enough experiences to see those patterns. So when people started asking those what-if questions and started finding those patterns and started writing it down and sharing it with others and other people, that gave them the ideas. Well, what if? So then you think about, wow, well, what is going to happen from here 500 years from now? Imagine. I don't know. It's a weird thing. We're only here for a little brief point in history, right? 100 years, usually. Most people don't live to be 100 years old. So you just got a little brief glimpse of human existence, which is humbling when you kind of think about it. Those are just those big what-if kind of pondering questions. So something to think about. Now, let's talk about this periodic table and everything that was in existence and why and the patterns and things that go with it. So just some review. It all starts with the atom itself, right? So when we discovered, or not we personally, when somebody discovered that there were atoms that made up something, and I think Democritus, was the first person who said this. He was talking about this theory. He said if I cut something in half and 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 in half, I would eventually get down to something called an atom that you couldn't cut down anymore. And I think it comes from the Greek word atomos, which means one, singular. atom, atom, okay? So when we're looking here, the atom has actually 3 parts that kind of all have to go together to make an atom. And what are those 3 parts? Neutrons, protons, and electrons. That's right. So we've got protons, so the atom, just looking at it, just to refresh our memory, we've got the atom is made up of protons, neutrons, and electrons. And these things, I use some symbols when I'm taking notes and when I'm writing notes. You don't have to use these. They're not really official. They're not in a textbook. They're not on EOCT or anything. But I do P with a plus, N with a little circle and a slash through it, meaning that's like a null set in math, right? That's just my abbreviation. And an E with a minus sign. Now, why would I choose the plus, the null set, and the minus sign?
Because the protons are positively charged, the neutrons are neutral, and the electrons are negative.
Exactly. These are positive, these are neutral, and these are negatively charged. That's why. Again, if you know that, you don't have to write that. You can put the plus sign, the minus sign, the neutral charge, or no charge. And then we need to think about their locations. Where are they in the atom? Okay, there's 2 things in the nucleus.
Protons and the neutrons.
Protons and neutrons. These both are in the nucleus. All right. Where are these electrons down here?
On the outside.
And what do you call that?
Rings.
Okay. So we put them on rings. We say they're on rings because they are on different energy levels, right? But what do you call that space that they take up? Electron cloud. That's right. So these are called, or we say that they're in the electron cloud. And I'm just going to abbreviate electron right there, cloud. All right, that's where they are. Now, we do organize them, on energy levels because they have a certain amount of space, but they really don't orbit in like a path, like a straight circle like that. They kind of go every which way, but they have certain areas that they can exist in. But their movements, I always think of, they're more like swarming like bees. Like if you hit a beehive and they come out and those bees, if they were assigned a certain area, these bees have to swarm in this area and protect the hive, and these bees have to swarm in this area. Kind of that same thing, and they make up this electron cloud. So just a quick diagram of where the nucleus is. Remember, the nucleus is in the center, so I'm going to put a P and an N in the center because that's where my protons and neutrons are. That is where the mass of the atom comes from, is from the nucleus. All right? The electrons, it actually takes about 2,000 electrons to equal the mass of just 1 proton. So electrons are really, really, really super duper tiny, even more so than the atom and the proton and the neutron itself. So super, super tiny, and they don't really affect the mass of it at all because they're so tiny.
Do we have enough technology to see them?
Well, on that, remember the video that I left for you the day I was out? You actually could see I think it was, they were making the bell, so it was you could see the atoms, that's right. So, and that is just, within the past 5 years that they've had that technology to see those atoms. And you definitely couldn't see where the nucleus and the electrons were. You could just see little dots that looked like a grid. And that was in that microscope kind of thing they had those panels that even sound waves would interfere with that.
Yeah, because he said that he could only get a 2D image of it. Like you could only see circles.
Exactly.
You couldn't even see a 3D.
No. But it was pretty cool just to be able to see because that's new. So here's what we're going to do. Jimmy Neutron has the atom for the symbol. So I'm going to place those rings right here like this, right? So it looks something like that. So you have those little ovals or those orbitals, sometimes called shells, and that's where your electrons live, and we say they go on those paths even though they kind of don't. But that whole area right there outside of the nucleus is called that electron cloud. So we've got the nucleus in the center, obviously, housing your protons and your neutrons, so that's your nucleus. And then you've got your electron cloud out here. And I just put little E's with little negatives. And it has a certain amount of space. All right, so that's kind of just the review. Now let's really talk about these electrons because I want to make sure you understand about the electrons because that's where we're really going to be talking about, when we start talking about bonding and we start talking about things like that, is really going to be about the electrons a lot. So we're going to come down here and talk about just the electrons. So talking about in that electron cloud on those orbitals. Number one thing about electrons is that they have energy levels. And sometimes those energy levels, we call them orbitals, or you'll hear them called as shells. Shells, energy levels, right? So they have certain areas where they exist. The more electrons something has, the more energy levels it has. Okay? So the bigger the atom is going to be as well, the more space it's going to take up. Now, electrons can be lost, they can be gained, or shared with other atoms. What's that process called when they lose or share or gain electrons? Is it what? Nope. Nope. What? Starts with a B. They bond together, right? So when you have a bond, it happens at the electron level. They're either losing or gaining electrons. Those are make ionic bonds. Or they're sharing electrons, and that's called covalent bonds. So there's two different types of bonds there, okay? So something's happening with the electrons. Nothing's happening when things are bonding. It's not happening with the nucleus, and it's not happening with the protons and neutrons. It's only the electrons that are causing them to bond or not to bond, okay? So the electrons in the highest energy level have a special name. Did you talk about those last year? It starts with a V, if that remembers. Does this look familiar? Valence. Do you remember that word? Yeah. Okay, so the valence electrons, I'm just going to abbreviate electrons. Valence electrons, those are the ones that are in the highest energy level. They are in the highest energy level. They might say they are in the outermost shell, or the last shell would also be appropriate there. So they're the ones on the outside ring, the outside shell, the highest energy level. Those are your valence electrons, which are different from your total electrons. And we'll get to that in just a second because we're going to draw some and work those out. So then we have something called stability. What does it mean to be stable?
To be,
Just stay the same.
Okay. So if you're stable,
Or to be like
you in good condition.
good.
you're in good condition. You're good. You're good, right? You don't need anything. You don't want anything. You haven't lost anything, right? You're good. You're stable. Everything's good. You're content. You're happy. You're not out there looking for something. Nothing's looking for you, right? You're good. That's what atoms want to do. They want to be stable, okay? And if they're stable, they have 8 valence electrons. All right, and this has a special name. So stability comes when you have 8 valence electrons. Stability, this is known as the octet rule. That's a weird word, right? When I wrote that down, I was like, is that the way you spell octet? You know, I was like, I don't even know. That looks weird. So the octet rule, what is the octet rule? What do you think it means? Octet. 8, right? It has something to do with 8. Like an octagon, has 8 sides, right? So that root word is in there. So what that means is that elements or atoms will combine so that they have, what do you think is going to finish that out? They have what? 8 what?
Electrons.
What type of electrons? Valence electrons. So they have 8 valence electrons. Remember those outermost shell. So they will combine, and when they combine, they can do that several ways. They can lose electrons, they can gain electrons, or they can share electrons. Okay? And they can do that. And when you have 8 in that outer shell, then you have satisfied their needs. They have needs, right? They want something. If they are missing, if they have just 7 electrons, guess what? They're going to do everything in their power just to get 1 electron. They just need 1 and they'll be happy. So they're going to do everything in their power to react with somebody who has 1 electron. And then they're going to go bloop, together, and they're going to bond. And that's a pretty neat thing. So now, what I'm going to do over here is I'm going to make a quick little chart about those energy levels, okay? So, there are 7 shells, okay? So here's what we're going to do. I'm going to say the shell, then I'm going to put the energy level, and then I'm going to say the maximum number of electrons. So max electrons that it can hold, the maximum number of electrons that it can hold. So there are 7 shells. Everything in existence, they can have up to 7 shells. And I will tell you about that in just a minute. But there are 7 shells that exist. So 1, 2, 3, 4, 5, 6, 7. And then they have very, very scientific names. Okay? They get a little bit difficult here. So you have the energy level of K is the first one. That's the hardest one to remember, but I'll show you what the rest of the names are. Isn't that scientific? You recognize that?
Yeah.
The alphabet, yes. Very scientific, right? So it starts with K and then just goes in order of the alphabet, okay? We are going to be dealing with the first 3 energy levels most of the time in physical science. This is prepping you for chemistry. And in chemistry, the fun part really begins because each of these levels has subshells, sublevels. So your chemistry teacher is going to have lots of fun with y'all with that. So we're not going that far. We're just setting up the foundation there. So the maximum number of electrons that they can have, this one can have 2, this one can have 8, the third shell can have 18, the fourth shell can have 32, the fifth shell can have 50, the sixth shell can have 72, and the last shell can have 98. Now, you don't have to memorize those. If I have to think about, well, how many can fit in this shell, I have to look it up, okay? And so you don't have to memorize that, but the 2, 8, 18, that's a pretty good rule of thumb. But remember, this third shell, if it has a third shell, if it has 8, it's stable. It can hold more on different energy, like on their subshells. It can hold more, up to 18, but it's stable when it has 8. It's not needing anything or wanting anything to be stable. It's stable when it has 8 on that outer shell. So we're going to be looking at and using this octet rule for stability more so than we'll be using this to know about the shells, okay? But they do exist, and this is how many electrons that they can hold, okay? Now, here's what we're going to do. I'm going to move on to the periodic table itself and elements. So tell me what an element is. Atoms make up elements, right?
We do this on the same piece of paper?
Yeah, if you have room. I didn't have room. But yes, if you have room, you can keep going. So what do we know about elements? They don't have 2 or more atoms. They only have 1 type of atom. Okay, and that's something that is important. So first of all, I'm going to use this term here. They are a pure substance. Now, if something's a pure substance, it's the same throughout. It's almost like if I drew a picture of an atom of gold and used the copy and paste button, if I could see inside, if I had a gold bar and I could see inside of that gold bar and see the atoms under that microscope, that fancy microscope they had in that film, if I could see that, then all of those atoms would look exactly the same. Like somebody took an atom and then pressed copy and paste, copy and paste, copy and paste, copy and paste. Okay? It's the same thing throughout. So they're made of 1 type of atom. Only 1. So in my bar of gold, I would not find oxygen. I wouldn't find an atom that's silver or platinum. I wouldn't find a molecule of water. I wouldn't find that in my bar of pure gold because it's a pure substance. The only atoms I would find there are atoms that are gold atoms. And it would have the same number of protons, the same number of neutrons, the same number of electrons every single time.
I just thought of something about alcohol. Like, does this have, alchemy? Is it the change?
Alchemy. Yeah, the alchemy is.
Actually possible.
No. Because alchemy was the study of people trying to change other metals into gold, which is not possible because gold is an element, right? So, but there was the whole scientists of the alchemists and things like that way back when they were trying to figure out, because gold was so precious. So a lot of people spent a lot of time trying to take other metals that they could find and change them into gold. But that's before they realized or knew that gold was one type of atom. Yes.
Don't you mix tin and something else to make bronze?
Bronze, right. Bronze is a little bit stronger. And when they mix metals like that, they're called alloys. Like, let's take gold, for example. Gold jewelry and stuff is not, because you have it weighted by carats, right? You have 10 karat gold, 14 karat gold, 18, 24, right? The higher the carat of gold, the more actual pure gold that's in there. But you have to think about it. You wouldn't want, like 24 karat gold's pretty soft. So you wouldn't want to wear something that's 24 karat gold all the time. That would be something that's special. It's more precious. It's more valuable. Like the wedding ring. I don't take off my wedding ring at all, anytime. If it was 24 karat gold, it would be softer and scratched up. So I don't know if mine's 14 or 18, but it's a little more durable because they take that gold, the pure gold, and then they blend it, they melt it down and mix it with some other metals that are more durable. They're stronger. They don't bend as much. They don't scratch up as much. And so, right, it's an alloy. That's right. All jewelry is an alloy. So there's no, you couldn't wear pure gold. Pure gold's very, very soft. You could,
Yeah. So if you got 24 karat gold and you push it really, really hard, it would bend.
It's softer. I don't know. I remember when I was growing up, they had those thick, I don't know what they call them. They were thicker chains, and if you had one of those they're not the rope chain, but they were flat, and they kind of interlaced like this, and really you could, you know what I'm talking about? And they're real shiny. If they were thick enough and they were real high, you could, indent it with your fingernail. So it's, it was softer. You wouldn't, and of course it's more expensive, so, just depends on what your purpose is of the metal that you need. But yes, if it's a blend, like bronze is not on the periodic table of elements because it's a mixture. Okay?
I was always wondering that.
Yeah.
Put it on there even if it wasn't mixture.
They put it on there if it was a mixture?
Yeah.
No, everything on there is made up of one type of atom.
Another table for mixtures.
They do not. No, there's no table for mixtures. There are so many, yeah. Most everything that we have is some type of mixture. You can't find pure elements in nature, even a lot of times. Even when you find pure gold, it's got stuff that has to be purified. It has to go through that purification process because things will naturally react with other things. Yes.
Like, I don't see why people with the gold, I don't see why they pay more for something that's not going to work. Like, that's going to dent and scratch more than
Right. Well, I guess it would all depend on your purpose. Do you want to have something, you know what I'm saying? Because it's very valuable. So sometimes people buy gold and have it as investments, like the gold coins and the gold. I don't know. I'm not that wealthy to even know how to buy gold. I'm a teacher, but it depends on basically your purpose. If you're wanting to make it an investment or something that you're going to pass down to your grandchildren and their grandchildren, you probably would want it to be more precious than a 10 karat gold something, that's less expensive or not as precious. So, it all depends on your purpose of what you're buying it for and how much money you want to invest and things like that. So, but elements are pure substances, so they're made of that one type of atom and nothing else if they're pure, okay? And they all are pure. We assume that they're all pure, even though in nature that we don't always find them in their pure states. And again, they make up everything in the universe. Now let's talk about that periodic table real quickly. And I'm just going to abbreviate because there's just a few things that we need to review to make sure that you remember about the periodic table. It organizes. What does it organize?
Elements.
That's right. It organizes those elements based on some patterns. Okay?
Atomic numbers.
And those all mean something, right? So it bases on those patterns. So just for the basics, you remember there are 18 family groups. Y'all remember that? Sometimes they're called families, sometimes they're called groups. I call them family groups so that we're covering all bases. So there's 18 family groups, okay, across the periodic table. And the family groups go up and down. They are your vertical lines, okay? So if you think about, they're the ones that go like that, right? And these are the ones that if they are in the same family group, they have similar characteristics or similar properties,
like noble gases have one missing.
No,
No, wait.
noble gases are all.
All the ones there. The other
That's
ones
right.
are the ones that don't have one.
That's right. Properties. Or characteristics, you can use that word too. They have similar properties. Just like you have similar characteristics and properties of people that, of your family. You may have, that Ancestry.com and those commercials and stuff talk about, generations and generations back and all kinds of stuff. You have similar characteristics as those. You're not the same person. You're not identical, but you do have similar characteristics and properties because you're in the same kind of family group, right? Same thing with those elements. Then we have also 7 periods. And these are your rows that go horizontal. All right? So the periods go across like so. And what this tells us is that if they're in the same period, they are going to have the same number of energy levels. So that's kind of an easy cheat. If it says, how many, looking at your periodic table, how many energy levels does phosphorus have? Phosphorus is P, number 15, so it is in the 3rd row, the 3rd period. It has 3. If something's in like cesium, which is number 55, how many energy levels does it have?
5, no, it's 6.
6, because it's in period 6. It's in row 6. And you can remember this. I always remember family. I think about taking a family portrait and people standing like your family, standing side by side, right? And a period you put at the end of a sentence, right? So a period, as you write a sentence, goes at the end. And we write sentences horizontally, right? We don't write sentences like this. So just to help you remember, that always helps me remember, okay? So there is a little bit about your periodic table. And then the next thing that we're going to put on here is about the box itself on the periodic table. So I'm going to draw a box. A boron. Boron is 5. And you've got different parts here. So this top number here is called the atomic what? Number. That's right. So that's the atomic number. And that atomic number is going to tell you something. What does it tell you about that element? How many protons. That's right. So this is going to tell me the number of protons every single time. Now, if you're talking about a neutral element, if it's neutral, which if it hasn't reacted and stuff, it's neutral, it will have the same number of protons and electrons, because positive and negative would have to be the same, right? And so that positive and negative stuff creates a force, like the positive proton in the nucleus and the negative electrons out here creates a strong force that keeps that atom together. It's like the glue that holds that atom together. So positive and negative. So if it's a neutral atom, it would have the same number, okay? But you can lose electrons, gain electrons, and share electrons when they react with other things. Now, of course, you've got the symbol and you've got the name, and then you also have down here, this is your atomic mass. The mass is a decimal number because it's an average, because boron can exist as this form, or it can exist with 5 protons, it can exist with 6 neutrons only. If you're looking at neutrons, it can exist with different numbers of neutrons. If something has a different number of neutrons, it's called an isotope, and we'll get to that. But right here, this atomic mass is the number of protons plus, and I'm going to write out the word plus, added to the number of neutrons, because that mass comes from that nucleus. So those are the two heavy things in the nucleus, the protons and the neutrons. And that's where the mass comes from. Okay? Now, the very last thing that we're going to look at before we go to some practice, I got some time, is a Bohr model. When we make models, you hate the Bohr models?
Ooh, I hate them.
And then you have a Lewis structure. They're not bad. Did you do both of them? Shoot, nothing. They're not bad. Nah. All right, so Bohr is named after Niels Bohr, and what you do is you place the symbol in the middle, B for boron. I just chose that, just because. And then you know that boron is in period 2, so it has 2 energy levels, right? Okay, so I'm going to draw 2 energy levels, 1, 2, and now I'm going to draw the electrons that it has. So the first shell right here can only hold 2 electrons. Even though there's more space and I could squeeze all the polka dots on there that I wanted to, I cannot do that in physical science or chemistry because it only holds 2. It's full. You have to go to the next shell. So it has 5 electrons, right? If it's a neutral atom, so I'm going to place 3 more on the outside. So that is on my uppermost shell, my outermost shell, the last shell. So I have shell 1 with 2 electrons and shell 2 that has 3 electrons. Now that the second shell can hold up to 8, right? Okay, but it only has 3, so it has a total of 5. Now for the Lewis structure, that's all for the Bohr model. For the Lewis structure, it only looks at the valence electrons. So how many valence electrons does boron have? 3. Okay? Because boron has 5 electrons. Okay? And 2 are on the first shell. They're protected. And then that second shell, those are the ones out there that are either up for grabs or ready to be shared, or they can pull some from somebody else on that next shell. So what I have to do for the Lewis structure is I do 1, 2, and 3. If something was full, like a noble gas, like neon, for example, if I was to do the Lewis structure for neon, neon has 8 in its outer shell. So the way I would do neon is 1, 2 at the top, 1, 2 at the right, 1, 2 at the bottom, 1, 2 at the left, and that's full. It has 8 in its outer shell. So if it's full, it looks something like that. Okay?
Because there's no circles.
But you're only putting the valence electrons. So they're either going to look like this, they'll look like this. You only have 8 dots to put on it. That's it. That's the one I like because it's easy. Okay? And I'll show you how to do the,
I thought there were 5 electrons in the boron.
In boron, there are. But this one,
It only shows the
no, we're not
Oh,
done.
you only do the outside.
We're not done. Yeah, we only do the one in the outermost shell. We're not done. So don't even go. They can wait at the door if we're not quite finished because we're going to do this. Yes. It's not bad. 3, 4, 5. Take 1, pass it back. 2, 3, 4. There's 1. 1, 2, 3. 5. I think there might be an extra 1. All right, there we go. All right, I'm going to show you how easy this is really quickly. And then I will dismiss you to go. But, so, again, if they start knocking on that door, y'all just hold on. All right, the very first thing is a review from your notes. And I'm going to go through this kind of quick, so y'all pay attention. It'll be on Google Classroom if you want to go back and check it later. All right, so the very first thing up here is atomic number, right? That's your atomic number. Then you have this, which is the symbol. Obviously, this is the name. And this is your atomic mass. All right, that's just labeling. That was in your notes. The atomic number equals protons, and I'm going to use my abbreviations. And this says or, and that's or electrons. Remember, it's only the same if they're neutral, because the atomic number is going to give you protons and electrons if it's neutral. Those electrons can change, but if I change that proton, I've changed the element. I can't change the number of protons. That atomic number is definitely always the number of protons. And sometimes it will give you the electrons too, but electrons can change. But all the ones we're working with today are going to be neutral, so those two numbers will be the same. Then the atomic mass is equal to the protons plus the neutrons, and those are my abbreviations. So now let's look at using your periodic table. We'll do oxygen and zinc on this side real quick. So the very first one here, it's giving you the square. Oxygen is 8. So if I did not know this was oxygen and didn't know what O stood for, I could look at my periodic table in order. It's number 8. And then I find the name, oxygen. And then I'm going to, for our purposes in here, what's the atomic number first? 8, right? That's at the top. Atomic mass, we're going to round. Always round the atomic mass to the nearest whole number just because it's easy and that suits our purposes in physical science. So that is going to be what? 16. Now, my number of protons and electrons, remember, are going to equal that atomic number, right? So those are both 8. That one and that one are both 8. Now for neutrons, I got to do something different. I've got to subtract. In this case, I've got to take the atomic mass, which is 16, and I have to subtract off how many protons, my atomic number, and in this case, I do get 8. Okay? But for zinc, it's not going to be that way. It's not going to be 888. It's not going to be the same all the way down. So let's do zinc. And if I don't know the abbreviation for zinc or the symbol for zinc, I can look at number 30. What is the symbol for zinc? ZN. And when you write these, be sure you always do capital then lowercase. It has to be that way because when we start doing chemical combinations and chemical compounds, a new uppercase letter is going to show a new element because a capital C and a capital O shows me carbon monoxide. A capital C and a little o shows me cobalt, which is a totally different thing. So be sure you're watching your capital letters. Atomic number for zinc is 30. Atomic mass, rounded, 65. Protons, 30. Neutrons,
25.
what? What? 35, right? 65 minus 30 is 35. And then electrons? 30. All right, so, and remember, we get this one from there, right? So 65 minus 30 is going to give us 35. Got it? Okay, that's the boxes. Hold up. Let me show you on this side how easy this one is. Super easy. Which atom is which? The only thing I have to do is I have to count the electrons because these are neutral atoms. So I've got 6 electrons. That's going to be my atomic number. What's number 6? Carbon. Good. This one, how many electrons do I have? Count your electrons.
1, 2, 3, 4, 5, 6, 7, 8, 9,
10 electrons. What element is that?
Neon.
Neon. Okay? That's how you do that page. This page here, we did boron on your notes. We'll do lithium really quickly. Lithium is number 3. It has an atomic mass of, what's the atomic mass? 6.94. I'm going to round that to 7. You can go ahead and round it. You don't have to put the decimal in. Now you're going to fill in protons and electrons are going to be your 3 and 3. Your neutrons, you have to subtract. 7 minus 3 is 4. Your Bohr diagram, your Bohr model. You put the Li in the center and you got to chart those electrons. So I've got 2 on the first shell. How many do I have to put on the second shell? 1. It's already got the energy levels drawn for you. Lewis structure, how many dots go out there? 1. Because remember, Lewis structure only shows valence electrons. Only the valence electrons. So the outside shell. That's exactly right. All right, good job. Finish those. It really won't take you long. Finish those.